today. So we were going beyond just relaxational critical dynamics. So we are trying to write down dynamical critical models which do not just include relaxation, so dissipative or diffusive relaxation terms, but also reversible dynamics, which in general you just do have. So you would in general have to worry about this. So the general Langevin equations we're worrying about is we're splitting kind of the systematic forcings in these Langevin equations into reversible and irreversible terms. We still have noise, and the relaxation terms are depending on if the modes we're looking at as alpha are conserved or non-conserved, looking like this. And then if we want the system to relax to thermal equilibrium given by a canonical Boltzmann distribution, we need to invoke an Einstein relation for the noise strength. So that needs to be related to this relaxation constant. Okay? This is one step. And then we have these reversible forces. Now we went through a little bit of formalism to construct, or I told you this is the form of these reversible forces. And the main input that we need here are these Poisson brackets or commutation relations that come from the microphysics of that problem. I was just motivating this. You can actually derive this form by means of what's called the Moritz-Zwanzig formalism. Just in case you've seen that, you don't just have to wave your hands. You can actually derive this. And then, as a sanity check, if this is my purported stationary equilibrium probability distribution, the least, the absolute minimum I need to demand is that the corresponding probability currents in the associated Fokker-Planck equation are divergence-free. Now that's at best a necessary condition, but not a sufficient condition for equilibrium, but it is a necessary one. So if that is violated, we're in trouble. So this is just a condition in this kind of formal space of dynamical variables as alpha of x, that the probability current, the stationary probability currents are divergence-free. Again, that is not, thanks for your question, this is not a sufficient condition, but it's definitely a necessary condition for any stationary behavior. And so then I was trying to make this a little more explicit and less abstract by looking at isotropic ferromagnets, where the reversible mode coupling term looks like this one, and really just describes the precession of local magnetization densities in the local effective field that's generated maybe by an external field, but also by the interactions with the other magnetization densities. So this is this form. And essentially invoking, I didn't quite make that so explicit, but really invoking rotational symmetry, you can fix the dynamical critical exponent in this situation by demanding dynamic scaling. That is not trivial, okay? It's one of the magical things why that works. And as I said, it's really a consequence of rotational invariance here. So this is the dynamic critical exponent for isotropic ferromagnets, and I showed you some experimental data that corroborate that. In the Halperin-Hohenberg alphabet, the relaxational models were A, B, C, D. This is model J. So there must be E, F, G, H. Let me in 2 minutes tell you what E, F, G, H are. Model E are planar ferromagnets. So you have an XY ferromagnet that's non-conserved, but it's coupling to the C component of the magnetization that is not critical, but is conserved. Okay? So there you have a two-component vector order parameter dynamically via basically these types of precession terms coupling to the conserved C component of the magnetization. That's model E. Model F is essentially a superfluid helium variant of that because the XY model statically is equivalent to a complex order parameter, and that's superfluid helium. If you take superfluid helium really seriously, you have to kind of add weird couplings to things like combined entropy and whatever densities that I forget. That's called model F. In more recent days, there's also a model F star. Don't worry about it, but it's very similar to model E. A bit more complicated. And then there is model G, that's isotopic antiferromagnet. So for an antiferromagnet, your order parameter would be staggered magnetization. Because magnetization, your spins would like to lie in antiparallel. but you still have the magnetization in the business, and it is still conserved. It's not the critical ordering field, but it's there. So for isotropic antiferromagnets, you have a three-component non-conserved order parameter that, again, essentially by such precession terms couples to the conserved three-component magnetization. For all these three systems, the dynamic exponent is again fixed essentially by rotation symmetry and comes out to be d over 2, and the critical dimension there is actually 4. While for the ferromagnet, the dynamic upper critical dimension is 6. And then there's model H, that's binary liquid or the liquid-gas transition. So there you have a conserved density talking to conserved currents. Well, by means of continuity equation, the longitudinal in position space current components are essentially the same as the density, so the transverse currents. We have to do some funny projections, and that's called model H. In that case, you actually only get weak dynamic scaling, it turns out, and you cannot fix the exponents exactly, so you can just compute them perturbatively. Don't be fooled, right, by both what Sid is doing and what I is doing. Of course, we show you models for which we know a little more than its standards. So, Sid shows you exactly solvable models that are fairly easy to do. I'm showing you some models for which by fairly simple arguments you can infer the dynamic critical exponent. That is not the normal situation, perhaps. Okay, so these are just the lucky cases that make these systems really nice to present in the school. So don't think that you can always just kind of wave your hands, do some scaling, and find these out. That is not generically the case. We're really happy when we find that. All right. So this is all I wanted to say about equilibrium critical dynamics. You can worry about what happens if you throw the system out of equilibrium and spend a couple of years doing that, but this is equilibrium critical dynamics. And then for the remainder of these lectures, today and tomorrow and half of yesterday, I'm going to go through some, in the same philosophy constructed, coarse-grained Langevin equations for scale invariants or non-equilibrium phase transitions in driven systems. Okay? So when we don't have thermal equilibrium and therefore have a lot more freedom to mess with the noise and other terms that we might want to add. And so the first one I was showing you is this driven lattice gas. Well, let's worry about that later while the guys fix this. So I showed you the driven lattice gas. So this is essentially biased diffusion of particles along one spatial direction, unbiased in the transverse directions. And they have hardcore exclusion, so cannot sit on top of each other. And then the combination of exclusion interactions and drive in a system with periodic boundary conditions, so we actually set up a non-equilibrium current system, leads to interesting, that is non-mean field, non-diffusive generic scale invariance. Diffusion equation is already generically scale invariant. We don't throw these big words at it usually. But in this system, we have a kind of nonlinear diffusion equation, which gives us a dynamic exponent that for diffusion would be 2, and this system is different from 2. Okay? Below a certain upper critical dimension. So the goals in this business that I'm telling you is we try to find a handle on the upper critical dimension. Maybe we can learn something about the exponents. Of course, there's a lot more information that I'm completely bypassing because it would be a lot more work. That is computing scaling functions. That can be done too, but that's considerably more painful. We actually need to do some calculations, which is not really what I'm doing. Okay, so in this system, we have to allow for anisotropic diffusion. This is the combined drive and hardcore interaction term. And so it comes with del parallel S squared. That's because overall the particle number is conserved in this system. So there need to be these del's in there that comes from the divergence of the associated conserved current. And this is conserved noise. So really this also was a divergence of some white noise was sitting in the current. And so if I write this in terms of correlations, it looks like this. As I argued, I can do one rescaling. None of these coefficients need to be the same as there, but by rescaling these fields S, I can make these coefficients the same. So I can kind of pretend I'm basically have an Einstein relation in the transverse sector, because after all, that one is just purely diffusive. But I cannot in generally make those equal. And so the ratio of C tilde and C tells you if you're in equilibrium or not. That ratio is 1. You know, it's really like an equilibrium system in the sense that at least the Einstein relation is satisfied. If this is not 1, then you're clearly out of equilibrium. And I showed you that shows up as funny singularities even on the Gaussian or mean field level for the density-density correlation functions in momentum space. You get singularity equal to 0. It's angular singularities. Nothing divergent, but you know, funny direction dependence. Since this is an isotropic system and it's generically scale invariant, we can write down this general scaling form. So we have a dynamic exponent, which I define in terms of Q curve. We have this overall prefactor. And then perhaps we have a non-trivial relationship between the momenta or positions, vectors, distances in the transverse parallel directions. That's characterized by this anisotropy exponent delta. But since the nonlinearity only lives to these del parallel, so if I restrict myself just to the transverse momentum space sector, this and this need to be the mean field exponents. So we know that for this system, the way I've written it, that eta equals 0 and z equal 2 are exact statements. So that's good because out of the 3 independent exponents, we already fixed 2. So we have one left, that's the anisotropy exponent. And that in this system, and again, it's good luck basically, we can fix that too by an emergent symmetry that this system has, which is Galilean invariant. So the original lattice model doesn't quite have that. But this continuum model is invariant under changing the fields S to S prime, where S prime is just going to a moving frame in a parallel direction. You can check that. We'll do an example in a minute. Straightforward. So the S by dt picks up that, the S prime by dt picks up this one, but it also picks up a d by dx parallel from there with ggv in front. And if I square this out, that is precisely the same term that shows up. So these things with a minus sign, so that cancels. Just write that down. It's a two-line calculation. So this is the symmetry of the problem. And then I was arguing by just scaling the different terms in here that we can actually fix the anisotropy exponent because it's just set. So this symmetry doesn't go away under the scaling distinction. And so that turns out to be 2 minus e over 3. And that also tells us that the upper critical dimension here is 2. So you get non-trivial scaling in 1 dimension, you get some log corrections in 2 dimensions. On higher dimensions, this is basically mean field on the exponent level, not on the scaling function level. Okay, so this is these driven diffusive systems. And a summary of what we did yesterday. Any questions? All right, so the plan today is to link this to other problems. And the first one is Noisy-Burgers equation. Noisy-Burgers equation is vorticity-free hydrodynamics, if you like, but with noise added. And we've seen this in earlier lectures. So if I write this down with a vector field du by dt, then I need to have some kind of convection term, advection term. So there is this gradient u squared. And then on this side, I have some diffusion terms, so that really is some viscosity. But I don't have curl terms, which you would have in the full Navier-Stokes equation. So I'm assuming that the curl is 0, or that del y uj is equal to del j ui, where ij are Cartesian components. And then I'm adding some noise, the average of which is of course 0. Since this is conserved fields, I have to write down, write me this one in Cartesian components. So instead of del squared, because I'm writing components, it's del I del j. And the usual product of delta functions in x and t, which I'm really getting too lazy to write. So that's the Noisy-Burgers equation. And for the fun of it, I'm going to add a factor dg there, which I can always do by rescaling, right? So you see that if I just change u to dg times u, nothing changes except that this u squared term picks up another dg. So I can arbitrarily put that in. That'll be useful to compare with this one later. I'm invoking some Einstein relation here perhaps. And I said kt to 1 because that also gets too boring to keep writing down. So that's the Burgers equation. And that's actually invariant under a Galilean transformation as well. Now, it really has to be, it's hydrodynamics. And so it takes a very similar to form to what we just had. Normally you would just have x minus vt, and then add an overall constant velocity field as I go to co-moving frame. And as I put in this dg there, I would have to put in this dg here as well. So let me walk you through this one and how that works. So if I do du prime by dt, t prime and t are the same things. This down. So of course I'm getting du by dt. But then I'm also picking up a minus dg and a gradient in x, which is then dotted into v. So I get a v dot nabla, v dot del, that acts in u just by chain rule from this first term, because there's a time dependence on the two, right? So this is just using this form. And then I insert the equation itself. So du by dt is this diffusive term, or viscosity term. Of course, somewhere we have the noise as well. Then we have the minus, I throw this on the right-hand side, minus dg over 2. And then del u squared. And we still have this term. So what I'd like to do is combine those guys to just minus dg over 2 del of u plus v squared. If I can do this, this u plus v squared is just u prime squared. And the del squared u is the same as del squared u prime. The second spatial derivatives are not really affected by this Galilean transformation. And so if that is true, I get the same equation for u prime that I get for u. And I've established that this is invariant, right? So does this work? Well, there's the dg over 2 del u squared, good news. There's the del v squared. V was a constant. That's just the uniform velocity that I'm doing my Galilean transformation with, so that's 0. But there's a del u dotted into v, which is not the same as v dot del into u. But it is with these integrability conditions or curl-free conditions, because the v dot, if I look at the ith component, it would be ui and then some vj del j, right? So ui and the del j, but according to this, I can write this as del I uj, and that gives me that term. So by means of the curl-free condition, this works out and we're in good shape. Okay, let's look at this in one dimension. There's no vectors, so the velocity field is a scalar. And if I make this into a scalar, and say call that scalar velocity field minus s, or I'm changing g to minus g, it gives me the one-dimensional version of this. In one dimension, I don't have these guys. I can call this C1. I need to be in the equilibrium version of that, so C tilde is the same. I get rid of this one. And in one dimension, this is just a del, d by dx squared, as we have there. And this guy sits here. And we are just having the same equation. So here I have this anisotropic equation for a scalar field. Here I have an isotropic equation for a vector velocity field. While in one dimension, that's just the same thing. So the noisy Burgers equation and this driven diffusive system in one dimension is the same business. That's great, because you just know the scaling exponents for this thing then in one dimension. We know that eta is 0, and the dynamic exponent that I have to worry about is the C parallel. It's the dynamic exponent in this one specific direction. And in one dimension, this came out to be 3/2. Right, so that's the C parallel here. So we see the Noisy-Burgers equation has, owing to this kind of advective nonlinearity, doesn't behave diffusively. It has anomalous scaling in one image. Well, we actually know a few more things, because certainly in one dimension, we expect this thing to be an equilibrium system. So in one dimension, we would think that the stationary probability distribution, the canonical distribution, should just be given by the kinetic energy of our velocity field. So that should just be e to the minus 1/2 integral u of x prime squared dx prime. Okay? So it's an equilibrium system. This is corroborated, yeah, this really means eta is 0 again, because it means that the static probability distribution here is just a Gaussian. And eta equals 0 is a fancy way of saying that. There is no nonlinear terms in the statics that would modify the scaling. Okay, so this independently would tell us that eta is 0 too. What now we can worry about is the Noisy-Burgers equation in arbitrary dimensions, actually in equilibrium theory. Well, it is, but is it one with the simple, just Gaussian velocity, kinetic energy in the canonical distribution? So arbitrary D, do we have this one? And so for this one, we can use what I call the equilibrium condition here, which is actually a slightly misleading word. So we have this necessary condition for the stationary currents to be divergence-free, not again sufficient for equilibrium, but necessary. So if this is violated, we have some trouble. We can check that. We can check for the reversible forcing term that we have here, which is really this guy. We can check for this condition. So we just put in a spatial integral in d dimensions, functional integral with respect to d by du, functional derivative. Then, of course, I don't need the constants here. Then come the del u squared. And I need to multiply e to the minus 1/2 and that integral. So here I should do x primes. Not to screw myself up. Okay? So we do the functional derivative of this, and so what are we getting if we do this? So that's the question, is this 0? So here, this is u del u for the 2, and so the functional derivative of that is going to give me a twice del u, so divergence of u. And you see that's a boundary term. So if I assume that my velocity field is kind of non-zero only on a finite volume, then I can view this boundary term, evaluate the boundary, and far enough out, this is going to be 0. So boundary term, so let's happily ignore that. Of course, you could come up with funny boundary conditions where that matters. Okay, I'm happily ignoring that. So this happily goes away. And then we need to keep the del u squared here. And do the functional derivative of this. So this gives me a minus sign. The 1/2 cancels. I just get a u down, and the delta function from functional derivatives just give me the u down. So this is what it is. And then I still have this term left. But the problem, this one is not a boundary term, and in general does not vanish. So in d dimensions, the kinetic energy is not just giving you the stationary, the equilibrium distribution. But in one dimension, things are just fine. So I look at this in one dimension, I have an integral dx. Here I have a d by dx, u squared, so the u squared by dx times u. Well, I can do an integration by part here, ignoring boundary terms. This is going to be u squared du by dx with a minus sign, so I'm just throwing the derivative onto here. But that one here is just minus 1/3 du cubed by dx. And that is a boundary term. So we're good. So one dimension is kind of special. It maps the Noisy-Burgers equation into this driven diffusive system. And it really is a simple equilibrium system where the canonical distribution is just determined by the kinetic energy of the scalar velocity field. So sometimes in this business, this is called a hidden fluctuation dissipation theorem for this system in one dimension. So I showed you this kind of picture for this driven lattice gas yesterday, where we had only hardcore interactions between the particle in the system. Now there's an intriguing variant of that that was invented by Katz, Lebowitz, and Spohn, where on top of that, hardcore interactions, you allow for easing interactions, nearest neighbor interactions, attractive interactions between the particles and the holes. Right? As I said, we can write this in a spin language by mapping the particles into, say, upspins and the holes into downspins. But on top of the hardcore repulsion, I'm adding attractive interaction between neighbors. If I switch the drive off, that's just the equilibrium easing model, say, in 2 dimensions. And I know that has a phase transition. And it turns out that phase transition survives if I switch the drive on. So now I have a genuine non-equilibrium phase transition that would take you from a disordered now in kind of distribution of these particles or the magnetization in the spin language, high temperature phase to a ordered low temperature phase. How does temperature actually enter? Well, for the hardcore particles, there's no temperature, right? So this was just bias diffusion. So once I allow for the easing interactions, I have to write down a Hamiltonian and do something like Metropolis Monte Carlo, where I get a bias if energy goes down. So I'm just essentially writing down transition rates that Sidney Redner was explaining to us yesterday. So on top of the drive, I get a new control parameter, which is this temperature. It's not really an equilibrium temperature because this thing is not an equilibrium system, but it's a temperature-like parameter. Or actually, it's J over T that is the real parameter, so the easing coupling divided by temperature. And then there is a critical point for that, which turns out to be roughly square root of 2. It's 1.41. I don't think people think it's square root of 2, but it's 1.41, the equilibrium or Onsager critical temperature where this thing orders. If this were an equilibrium no drive, what you would see, since I have a little bit of bias with these square lattices, you would get ordering into stripes either this way or that way, and then you would get coarsening again, as Sid very nicely explained to us yesterday. In this non-equilibrium system, the ordering turns out to be only stripes along the drive direction. So the spatial rotation symmetry here is broken by the drive, which is not surprising, but you get stripes ordering along the drive direction. You get coarsening in the low core temperature phase, but it's extremely slow and painful. My Virginia Tech colleague Roy Sears literally spent years on trying to analyze that. So it's very, very slow coarsening. We are not going to focus on that. We're going to focus on the critical dynamics right at this non-equilibrium phase transition. Now notice this is quite intriguing because of course at the phase transition we are going to have scale invariance and dynamic scaling and all that. But in this system, in the entire disordered phase, you have scaling too because that's just a DDS generic scale invariant system. So what you're seeing here is a change in scaling exponents as you go from the high temperature phase onto this non-equilibrium critical point. Okay? So it's a cute model, and it turns out we can, it's again this unusual situation where we can actually fix the scaling exponents exactly by symmetries. So I quickly walk you through that. Shouldn't take that long. Thank you, upstairs. Yeah, I don't have the control panel here, so I need you to. So this is the Katz Spohn model, KLS. And as I just said, there is a critical temperature with a non-equilibrium continuous phase transition. And we'd like to describe that. So once again, I feel a little awkward here because John Cardy actually invented the corresponding continuum description, many years ago with his student, and independently Schmidtmann and Janssen did. But we have all the ingredients, so it's actually fairly easy to do. We need to somehow marry these drive terms here, which are not going away, right? We still have the driven lattice gas, so we certainly have these kind of nonlinearities in the business, with essentially model B for conserved order parameter, which shows a phase transition. Okay? So I need to write down essentially a model B equation where I'm allowing for spatial anisotropies and this drive term. Well, I need to be a little more careful than that because I just told you ordering only happens in stripes along the drive direction. So if I think about, is my longitudinal spatial sector critical or is it the transverse sector? It's the transverse sector. Because in the longitudinal thing, everything just kind of looks and does its thing. But transverse, I get modulations. So the system orders in the transverse direction. I want to only describe the critical fluctuations, so I really need to worry about the model B terms, such as the gradient terms that come from some effective Hamiltonian maybe, and the nonlinear terms in the transverse sector. I can treat the longitudinal sector essentially Gaussian, except for this drive term. Okay? So let's write that down and see if that makes sense. So we're going to write down a continuum, coarse-grained, non-Langevin equation that captures phenomenologically these features. So I'm doing the S by dt. I allow for anisotropic diffusion. So there is another diffusion term here. That would be this one, but now this transverse sector is critical, so really the first order term is that goes away with T minus Tc as in model B. And I need to keep what in model B came from the gradient terms of the Landau-Ginzburg functional. So this is model B-like, but only in the transverse sector. This is just the diffusion term times S. Then I need to write down this drive term, which I'm just copying from over there. So the nabla parallel S squared. And then I need to write down the model B nonlinearity, which is living in the transverse sector and knows about S cubed. Because that came from a S to the fourth term in effective Hamiltonian. So these things are coming from the Ising part, and then we have some noise. And the noise looks essentially like over there. And so you have two competing nonlinear terms. So we see that we have a spatial anisotropy in the Gaussian correlations already, as you would expect. And then we have two competing nonlinear terms. So for those, you need to do some kind of power law scaling, dimensional analysis to see which of those matters. And it turns out, although this has been a little bit controversial for some time, that this thing is irrelevant near the transition. And that is because it turns out that this coupling here has a critical dimension of, if I could remember that, 5. And only with the transverse sector this would have 3. And it turns out that the larger critical dimensions, once you get direct competition, always win. So there is a renormalization group argument that allows you to throw this away. Now, this coupling U, or U perpendicular to be careful, it really is a dangerous irrelevant variable because it's driving the transition. Let's not forget that. Without this thing here, there wouldn't be the transition. So you can throw it away if you compute scaling functions and the like. But this term does not enter when you compute critical exponents. That's what I'm after. Okay? So you really need this term to have the phase transition, but it does not affect the computation of critical exponents. Right, then we can stare at this. And again, the critical sector is the transverse one. But the only nonlinearity left is in the parallel sector, which immediately tells me if now let me first write down the scaling form and then we can look at. So this is a little bit different to this scaling form because we now also have the critical temperature in the game and so model B scaling. And that picks up another factor of C conventionally in front here. And then we have scaling functions where we have this critical variable in the game with the correlation length exponent 1 over mu. We still have an anisotropy exponent. And we have, of course, a dynamical exponent. I'm defining these ones here and eta in the transverse sector. So, since the nonlinearities only live in the longitudinal sector, 3 of these 4 exponents are mean field to all orders and exactly. So we know that eta is 0, mu is 1/2, and C is 4 exactly. 4 is because, it's basically model B scaling, conserved order parameter. So that follows from these definitions. And then we need to worry about this anisotropy exponent, delta. So mean field value for delta is not 0 in this case, but it's 1. And you can kind of see this here. I have del parallel squared that I need to compare with del perp to the 4th. So Q parallel scales as Q perp squared. On the Gaussian level, the anisotropy exponent is already 1 here. The way I've defined it. So this system 2 obeys Galilean invariance. We can show, well, it's kind of obvious actually, because this Galilean invariance was just doing things in the longitudinal direction. And in the longitudinal direction, x parallel, this looks just like the Noisy-Burgers equation or the Stirling diffuser system over there. So I still have this form of Galilean invariance that I can invoke. And then I can walk through this and check for scaling, which I won't repeat because it's really the same kind of algebra that we went through yesterday. And you find that the anisotropy exponent is fixed by demanding that the symmetry survives under scaling to be 8 minus d over 3. In this case. Okay. So the mean field value is 1, which is reached at 5, which is, by that comes, critical dimension is 5. And then with this one, you can write down all kinds of other exponents, and the system is fully characterized. So one more example where that's actually possible. Yeah, if you go back to how this looked for model B, it had the same thing in the dynamical correlation. So that's where it comes from. It's sometimes a little subtler where these are included and where not, but it turns out to be that. It doesn't show up for this system because it doesn't have a critical point. So it's just, in a sense, it's also a definition. Right? Okay, other questions? the question was why is here said and it's not over there, and partially that's convention, and convenience, and how you want to define things. All right. So I'd like to go away now from these driven diffusive systems and look at driven interfaces. So heading towards things like the Cardy-Chang equation. So they are the mean field exponents, but they're also true to all orders. What happens in 2 dimensions is delta is 0, but the corresponding scaling picks up log corrections, logarithmic corrections, which is kind of what happens if these things go to 0. That means logarithmic corrections. Likewise, over there, delta and C parallel, and these things pick up logarithmic corrections, but the transverse exponents don't. Yes, so for example, right, so this was defined here in terms of this Q perp. If I wrote this with Q parallel, I would have a C parallel there. And I would need to scale that. And the C parallel comes about by replacing these. So C parallel, as it was over there, is the C perp, which I didn't write down in index, divided by 1 plus delta. So while the transverse sector is trivial, Gaussian, the longitudinal one isn't, because this delta carries non-trivial fluctuation correction. And again, in 2 dimensions, that would lead to log corrections. So over here it would lead to log corrections in 5 dimensions, because the critical dimension is 5 here. I'm going to motivate the KPC equation twice with a little bit of hand waving as usual. And the first motivation is we look at a driven interface or domain wall, say in an Ising magnet. So schematically, we have some substrate vectors X, and we have some kind of domain wall that has some fluctuations, and with some external field, I'm going to call G, I would move, say, this domain wall in the direction up there. So if the field is positive, I would go from a positive Ising domain here, negative Ising domain there, and this domain wall would invade the negative magnetization domain. So let's try and see if we can kind of model this. What we're going to do is we're going to describe the interface function here by this height function, which is a function of this kind of d-dimensional substrate, vector x, and time, and I'm assuming I can neglect overhangs. So I'm assuming I don't have to worry about such things. So I can write down a well-defined height function. On a sufficiently coarse-grained level, that should be okay. If I look on the level of individual lattice sites, certainly not. There will be these overhangs. But the assumption is if I coarse-grain sufficiently in a sufficiently large system, I can do that. I can neglect these kind of things. So I get a unique height function. And then I write down an interfacial energy. So this would come with some surface tension. We call that sigma. My interface is a d-dimensional object. So that really is again that's already the area, d-dimensional. And then I would need, from differential geometry, I would just need 1 plus gradient h squared. That gives me the local curvature, and that is what I need to. I'm going to ignore this and call that 1, or sigma by kt 1, so I don't have to worry about it, but it's of this form. So if I have kind of small fluctuations, then I can expand this, and of course I get getting a constant, which is the surface area, and then I get something like 1/2, and the integral of del h squared, which looks a bit like a kinetic energy. Okay. Then I'm going to write down some relaxational dynamics for this, but I'm going to assume that the relaxation rate itself depends on this kind of local curvature like that. So I get curvature-driven growth. So I'm going to write down some dH by dt with some relaxation rate d, for which I assume this term shows up too, otherwise I just have a linear equation. And then I do minus dH by d little h. So this is relaxational kinetics, model A kinetics if you like. And I add a drive term. And I'm assuming again the drive term is also favored. There's more growth where the local curvature is in place. So that's all the assumptions in here. Okay? And then this is a stochastic system. So we throw in some Gaussian white noise. Gaussian white noise just because it's the simplest thing to do. And so dH by d little h under this approximation is just with a minus sign, right? So do integration by parts. That's just going to be the Laplacian of h. Right? This is minus h Laplacian h, so I just get Laplacian down here. So if I expand again for small arguments, the first one I have is this kind of diffusive flattening, which is induced by the surface tension. The system really doesn't want to be rugged. It wants to be nice and flat to minimize surface tension, interfacial energy. Then we have the drive term here. Well, that's just an overall constant, and it just tells me where the mean location of the interface is. I'm going to get rid of that by a Galilean transformation, going into a co-moving frame with the mean position of the interface. Then I get 1/2 dg gradient of h squared. That is the nonlinearity that's induced by curvature-driven growth. Yes, you're right. I keep saying curvature. It's just right. It likes when there are these things, it likes to grow preferentially there. All right, so basically there, we just go to co-moving frame, where we subtract the, if you like, ballistic growth of this height field, and then in my notation, and with a little bit of rescaling, we end up with this KPC equation. And the rescaling I can do is just to pretend there is an Einstein relation with KT equals 1 between this diffusion constant and relaxation rate in this. Now, remember, initially this was just model A dynamics. So there's nothing conserved here. I don't have to do that. And most people write down the KPC equation with a different where they call this D, where they call this nu, and they call this thing lambda. In the general philosophy of how things are done in critical dynamics, you would not actually do that because you rescale fields, so you get rid of one of these coefficients. Write it in this way, and if you write it in this way, G is actually already the correct effective coupling. So there we are. So this is the Cardy-Parisi sign. You can also do this via surface growth, and I'm going to do this even quicker, which was the original motivation. So here you would have a growth velocity that you demand depends on gradient of h. Because h itself shouldn't matter, but local bumps should. So now you expand in this argument. So there is v of 0, and then there is gradient v dotted into gradient h, and there's the next coefficient I call dt over 2, just a Taylor coefficient that I'm calling this way, and I stop. And ultimately add some noise. And I get rid of this overall constant and get rid of this one too by slightly more involved Galilean transformation. So here I'm writing S of x in t is h of x minus del v times t, t minus v of naught t. So the constant one I get rid of in the same way as here, and I can get rid of the linear term by just that transformation. And then these things go away, and I have to add some kind of diffusive flattening. So that's a surface reconstruction, if you like, that particles pile up, but on occasion they can fall down and move about and flatten the surface. So add diffusive reconstruction or something like that, flattening. And we end up at the same equation. And you can come up with at least another dozen of physical systems that can argue are described by the same distance. Yes. So this is a Taylor expansion, right? So this grad V is evaluated at h equals at grad h equals 0, so it's just a constant. So here that works. Yeah, so I'm always a little nervous by this because ultimately, as we see, we're going to look at surfaces that are actually rough, right? Where del h squared is anything but small. But in the original derivation, we have assumed it's small. So there's a bit of an inconsistency there, and we can argue forever about that. I'm just repeating. So I'm a little nervous. I'm not convinced that the KPC equation really does have to really describe the rough phase. We know it does describe the transition to it. We'll get to that. But I'm not convinced it does really necessarily have to describe the rough phase, because I think its internal assumptions in when it was constructed actually breaking down there. But I'm in a minority opinion camp, perhaps. But as I say, the kind of description, so the description you're using is kind of small, but I would think actually you would, if this gets really big, you really have to go back to these situations and take these square roots carefully, which are all order terms. So you have to do something that's in the spin language equivalent to things like nonlinear sigma models, right? Where small fluctuations are not doing the job. You have to properly fix the constraints, but no one's done that. And it's hard because it's a square root, right? So it's ugly. What we are getting. Sure. I'll show you in a second, I think. Ask me again. Well, it goes with the roughness exponent as positive, so there's large explosions, right? Yeah. Yeah, all that may go down the drain. All right, so I think I'm kind of lucky out here. So if we now compare those two equations, and we write down something like, where do I do this? No, I want to, anyway. I inevitably have to erase something I'm going to need, so let me erase this bit. So I may keep the Burger's equation and that equation here. And actually, before I get there, let me look at the linear version, because then things are clearer. Let me look at the linear version first here, which is g equals 0. In this context, this is really just a noisy diffusion equation, right? But in this context, it comes with a separate name called Edwards-Wilkinson equation. But it really is just noisy diffusion equation. And for that one, of course, it's a Gaussian model. It's really like critical model A. Critical Gaussian model A. Because all we have is, there's no mass term, so things would be generically scale invariant. We have diffusion, this guy's away, and that's it. And so we know for this system, these are our scaling exponents. It's a fancy way of saying we're looking at the diffusion equation. We know more than that because in this case, we also know this is effectively an equilibrium system where the stationary distribution is really just given by this interfacial free energy, right, in the approximation of small height fluctuations. So it's just that. Integrated over the in the context of these surface growth models, However, people don't like to use this eta somehow. That's just when scaling theory for these was historically written down first, they define something called the roughness exponent. So you look at 2-point correlation functions for these height objects, and you define that these things grow with x to the 2 chi, and then you have dynamic scaling with t divided by x to the z. So this is in our standard language, this one isn't. We used to write down instead something like 1 over x to the d minus 2 plus eta. Just to find our eta. Okay? In the language of these interface fluctuations, this is defined, and what this is saying that if you are at times smaller than the scale, and forget this, you see that the interface height fluctuations grow with distance if chi is positive, and then chi is called the roughness exponent. So if chi is negative, fluctuations die out, and you call the interface smooth. 0 is marginal. If chi is positive, you're in the rough phase, and that's what we were just discussing. So what we see here is we can read this guy off, because chi is just d minus 2 plus eta in my standard notation divided by 2. And we've just seen that eta is 0. It's just d minus 2 divided by 2 in this Gaussian model. So it's negative in dimensions less than 2, and the interface is flat, and it's rough in dimensions larger. Okay. But I got the signs wrong. This comes with a minus sign, so 2 minus d minus eta. So in dimensions less than 2, the interface is rough. In dimensions larger than 2, it looks like it's flat. Okay. Now there's a cute scaling argument, again before I go to that connection, that relates the roughness exponent with the nonlinearity in play now with the dynamic exponent. So now we have that, and the argument goes as follows. We are looking at some kind of blob on the interface of size, say, Lx along the substrate and of height Lz. Now what we know is that this Lx of t is supposed to obey dynamic scaling with the dynamic exponent t1 over z. According to this definition here, the height-height correlations grow as x to the 2 chi. So the typical heights, which is this Lz, should scale as Lx to the power chi. Now things are supposed to be growing. So this blob will be growing in time, driven by these gradients of h, so proportional to Lz over Lx. Okay, so this will be this height-driven growth. And so with this scaling, that means this goes as Lx to the chi minus 1. So in terms of time, I can solve this simple differential equation with a power law. And you find that Lx of t should grow as t to the 1 over 2 minus chi. And to integrate that just gives you 1 minus chi, 1 power added. And so then you compare those two, and you would conclude that z plus chi should be 2. When these nonlinear terms and these local overhangs, so this is the thing that's driven by g, are important. Okay, after this, let's go back here and write the vector field in the Burgers equation as the negative gradient of our height field S. So I'm just applying essentially a gradient to my KPC equation. So I get del du by dt, I get the diffusion term, and here I just get dg over 2 overall gradient in front and u squared. So same equation. So these things by this mapping are the same equation. So then we have this funny Galilean invariance that we have for the noisy Burgers equation. What does that translate to here in the KPZ equation? Well, we basically need to integrate this thing for, say, small fluctuations. So now we get a local symmetry where S of xt gets replaced by S of x prime t prime, which is my original S, with the same shifted coordinates as in the Galilean transformation. So it's kind of in the middle there, x minus dgvt. And t. Here we were just adding a v. So with this minus and integrating, we need to subtract a v dotted into s. So then if I do x, then if I do the gradient of this, I get back to there. And then if you think about what this means is v is really a tilt of the interface, infinitesimal tilt. Right, so I'm infinitesimally rotating our interface, and of course that shouldn't change the physics. So Galilean invariance is really like a tilt symmetry. Okay, with that tilt symmetry, we can actually recover this scaling relation between this dynamic exponent and the roughness exponent. Because what we see here, if I look at the magnitude of v, that should scale like s over x. S, again, because this is an SS correlation, should scale as x to chi. So this is x to chi minus 1. On the other hand, if I look at the argument here for the Galilean transformation, that's x over t. So that's x to the 1 minus c by dynamic scale. And because t scales at x to the c. And so if I compare those, I get back to we actually know a lot more if you look in one dimension, because we just saw that we know all the scaling exponents for the Burgers equation in one dimension. But the Burgers equation is, the same as the KPZ equation, so we know the KPZ scaling exponents in one dimension. And so specifically, we know that C is 3/2. And then, according to the scaling relation, that tells us that the roughness exponent is 1/2 in one dimension. And it is 0. This isn't just true in theory land. They're very nice experiments, actually quite a host of them, that give you that scaling. Let me show you one example, if the technical stuff up there helps me. Please need the projector on, and thank you. So one-dimensional interfaces. You can force things to grow on a substrate dimension, just kind of on a planar surface along one direction. So once the light comes on here, what I'm showing you is data for silver electrodeposition from an aqueous solution on function of length and function of time scales. Of course, the trouble is, if you do this in surface growth and you want to try and find power laws, you do not have decades of available phase space available. You can't really grow a surface from micron to kilometer scale. So they only have a couple of millimeters to centimeters, and that's what you see here. So there is a scale of maybe 2 decades, and then what they see is a growth. They call the roughness exponent alpha in this picture. And you see that up here we get this nice square root behavior in the log-log plot. They also kind of show the morphology of what they're seeing. So in this low regime, you get kind of structures that look a bit more like DLA, diffusion limited aggregation, or things like that, fingers and what have you. But once there's, the growing interface is sufficiently compact, you get this morphology. But if you look carefully, as I was emphasizing before, on small scales, of course, there's all kinds of non-unique height functions. There's all kinds of little overhangs. So you have to do a bit of coarse graining across here. Not too much. If you coarse grain too much, everything's gone already. So it's a bit of an art to do. But that's what they're getting, and and of course it's a bit of noisy data. Then you can translate it into time scale. If I relate this into time scale, I get the ratio of these things, so 1/3, and this is sometimes called beta. So beta is just the ratio of chi divided by z. And that's showing here, and they get fairly decent scaling over maybe 1.5 decades, not much. That exponent, so not bad. One of the cleanest ones of these actually happens in turbulence, done in Japan by Takeuchi, where he's very carefully found the KPC scaling exponents. That's probably the cleanest experiment. On the more fun side of things, you can burn paper. Some of the people in Finland have just burned sheets of paper and followed the flame front, and that obeys KPC scaling. It's a very, yes. Very good. Thank you, Sriram. Yes, it is. And the reason why that is actually precisely the mapping to these lattice classes. So this is actually what, I didn't really have time to talk about these aging things a lot. So that's non-stationary behavior when you're not in the stationary scaling regime, right? It's the initial regime. I did mention that for things like Model B with conservation laws, the aging exponents are given entirely in terms of the stationary exponents. Because you have a conservation law for these driven diffusive systems, that's there true. That's true there too. That's what I want to say. And in one dimension, that translates directly to KPC, so it's just fine. But it's a non-trivial statement, absolutely. But it does work. Good point. Bit subtle point, but very good point. Thank you. All right. I think I'm good with this one, so we can slide this back up. So this is one dimension. There's a lot more things known in one dimension for the KPC equation and or these driven diffusive systems in TASEP, because people much cleverer than I have figured out how to solve the actual problem exactly. People have computed lately scaling functions for these things in much detail. And so there's a lot of things known beyond just these scaling exponents. So what happens in higher dimensions for the KPC equation? So that's actually quite intriguing. And the way I'll try to explain that is by looking at the coupling versus dimension. That's a very statistical physics plot. We pretend dimension is a continuous variable, and I'm looking at, actually, this would be a fixed point coupling in some RG. To make actual sense of that, but let me still plot this. So what happens is, this system has a critical dimension 2, which we can kind of see from here. Okay. That critical dimension is, however, not really an upper critical dimension. People have been confused quite a bit about this. It's not. Okay. So but it is an important separating dimension. So if I'm in 1 dimension or 0, which you can kind of solve exactly too, that's substrate dimension. So this is the typical physical situation that you're in, either here or there. Then what you find is that this fixed point here behaves like this. So this one here describes the scaling exponents, chi 1/2, c equals 3/2, and what have you. Generic scale invariance. The surface growth is obeying generic scale invariance for some exponents, and in 1 dimension, that's the values. And what you find if you analyze the system is that the corresponding fixed point coupling that describes this actually diverges in 2 dimensions. And we think that's true to all orders. And then it comes back here at 0. Okay? But the character changes. Here, this is an attractive fixed point. Here, this G is repulsive. So there it describes a phase transition. So what we have up here for D larger than 2 dimensions, we have what's called a roughening, non-equilibrium roughening transition. What does that mean? If I'm in regimes where my nonlinearities here are small, compared to this, I'm driven down here where G goes to 0, so I'm going to the Edwards-Wilkinson case, which is a flat interface in more than 2 dimensions. So here I have a smooth phase. Okay? You see that the 2-dimensional case is kind of marginal and therefore not really easy to address. If I were in 2 plus epsilon, I can do this. If I start with stronger nonlinearities, I'm driven to, perturbatively at least, infinite G. And so that is a really rough phase. And then there's a critical line that separates those 2 phases. So what this critical dimension really is a lower critical dimension for the roughening transition. So I should call this the LC. It's the lower critical dimension, which separates dimensions for which transitions are possible. So for D less than D2, I do not have the roughening transition. All I have is generic scale invariance, which we know a lot about it in 1 dimension. For D larger than 2, I have this roughening transition. I know everything about the smooth phase because it's Gaussian. Perturbatively, I know nothing about the rough phase. But people have applied non-perturbative RG, calculations to that, which of course are approximative too, and they find fixed points and scaling exponents and the like, and they seem to be still satisfying C plus chi is 2. There is not really a reason for that, because C plus chi equal to 2 does technically require that the fixed point value is finite. But, it seems to work. But here we have this roughening transition, and now we can worry about the critical scaling exponents at the roughening transition. Now, admittedly, this is slightly, academic because that shows up in more than 2 substrate dimensions. So we can't easily do that in experiment. We can still worry about it. And the cleanest way of doing this is mapping this problem to yet another one, which looks entirely different, and it's actually an equilibrium problem of a disordered system. Well, that gives us insight into the roughening transition. And so I think I can do this in 10 minutes. Of course, that's the beauty sometimes of theoretical physics, when you're able to relate very different problems with each other and just steal kind of known results from different fields. So we're going to look at a directed line, think polymer, think maybe flux line in a type 2 superconductor, but a single one, in a disordered medium. Disordered medium means I have some random potential, which is sometimes attractive, sometimes repulsive to this line, with mean 0 and some non-zero Gaussian variance. So pictorially, although this is hard to do, we have this kind of substrate dimension again. Let me call this y. And then we have a z direction that I call s. And I have kind of my directed line in here that moves. Starts, say, at 0. And let's have it end up at position x. And let's have it end up there at height t. Okay? And then the random medium, you could think of some randomly scattered point effects or something. So this line likes to attach to the attractive versions of those. Okay? So there will be some surface tension for the line. The line will try to be straight. That's fighting with this pinning. So you get competition between pinning and elasticity and thermal fluctuations, which will give some thermal wandering. So let's write this down in thermal equilibrium. And what we write down is basically something like a partition function, where this line starts at 0, ends at x, and at height 0 and ends at height t. So what is this? We have a constrained integral. We need to sum over all paths y of s that take us there. And we weigh the paths exponentially by some Boltzmann factor that knows about the energy. So what's the energy? Let me just call that h qt and write the Hamiltonian down here. So this goes, that's an integral along the line contour, ds. It has line tension. And I'm going to write this in this linearized form. I could write down the differential form for this again, which is the squared as we had before. But so here we have a linearized line tension epsilon. And then when the position changes is function of height, I'm paying energy, so it's not straight. And then I have the pinning, which depends on lateral positions and depends on height. Right, so this is my random potential, and I assume that the mean is 0 and the variance is some Gaussian. Comes with delta and x minus x prime, comes with delta t minus t prime with some strength, which I'm too lazy to write down. So this is just the partition function for that. Right? Single line. Now you might have heard before, if not I'm telling you now, is that of course the partition function of a line-like object in statistical physics is formally equivalent to the quantum mechanics, well, Wick-rotated quantum mechanics of a quantum particle that moves in time, which is why I called the high T. And the way that works is because, if you look at this Hamiltonian, if I replace minus 1 over kt by I over h bar, then this looks like a Feynman path integral for a quantum particle, where this would be the Lagrangian. This is like the kinetic energy. S plays the role of time. And this is a potential, quantum potential. Okay? And there's some signs wrong. This is in statistical physics, that's a Hamiltonian, so it comes with kinetic energy plus potential energy. But once you do that big rotation where you replace S by minus T, the sign is properly changed and it ends up to be looking like a Lagrangian. All that works out just fine. So this is like an imaginary time path integral for a single quantum particle with mass epsilon. Right, that's the mass. So line tension translates into epsilon. I over h bar needs to be going into minus 1 over qt. And it's in a random potential. And the random potential is a randomly fluctuating potential. This is random in space and time. So my particle travels, so this is like the particle world line now. Particle travels along, and as it travels along, potentials, these point potentials are switched on and off. Or this landscape is switched on and off. So it's a weird quantum problem, but it is a quantum problem. Which means equivalent to this path integral, I can write down a Schrödinger equation. So I can write down the corresponding imaginary time Schrödinger equation. I don't need the analogy, I can just write down the Schrödinger equation directly, you can check that. But the analogy helps because it shortcuts things. Instead of IH bar, psi by dt, I get kt dz by dt. Okay. Then I get minus h bar squared over 2m, and then d psi by the x squared. Well, with the minus signs that come up here, the h bar squared becomes kt squared. Minus sign is eaten because there was an I in here. And it comes with twice the mass. And it comes with the Laplacian of partition function. Then, of course, I have the random potential times the partition function. So that's the equivalent Schrödinger equation, same thing. So if I can solve this or solve that, I solve the same problem. Okay? All right. Next, we do something that's kind of stolen from the analysis of the Burgers equation, is what's called a Kohl-Hopf transformation. So that's a nonlinear transformation where you write essentially down the free energy. So we take kt log z, but just put some dg epsilons in front, just for the fun of it, and a minus sign. So really this S is essentially the associated free energy. If I then look at the equation of motion satisfied by this S, by exploiting the equation of motion satisfied by Z, you're getting the KPC equation. Okay. You get the KPC equation with noise, which is related, of course, to this random potential. So the random potential just translates into our dynamical noise. And the KPC, so the free energy for this line problem essentially satisfies the KPC equation. With this, we can make a, so what happens now in terms of this roughening transition? It's especially useful now for this roughening transition business. So I was telling you in the equilibrium language, we have competition between line tension and pinning and fluctuations. So the smooth phase is when pinning is kind of irrelevant and line tension wins. Line tension will keep this line straight, and that corresponds to smooth interfaces here. Then there's a phase transition, which is like a vortex glass transition, where you go to a disorder-dominated state, where the line is rough, and pinning dominates over the interfacial tension, line tension. Okay? So now the rough phase is the disorder-dominated state, and the smooth phase is when disorder is kind of irrelevant. And then so here is argument that goes back to Kim and Kosterlitz. That's my Kosterlitz of recent Nobel fame. And their argument in a very short letter without any calculations was that if I'm at the transition, at the roughening transition GC, call this GC here, then you should be in a marginal situation. So they just said, well, it's disorder dominated in the rough phase. It's certainly smooth in the smooth phase. So right at the transition, we're still seeing the smooth answer. Since chi plus z is 2, that predicts that the dynamic exponent at the roughening transition itself should be 2. What you can do on top of this, I don't think they did that, but you can look at some typical length scale that you can generate. Story. And this is like an expansion, as I said, about the lower critical dimension. So you find that the correlation length exponent in this business should go as 1 over d minus 2, as it tends to do for these expansions about the lower critical dimension. So this thing diverges at the lower critical dimension as it's supposed to be. These answers are believed to be the exact answers for the roughening transition. Now, a historical note, I spent a lot of time with a good friend of mine to check this. It's obviously, it's easy to show that's true in a one-loop perturbative calculation for the KPC equation. We did this in a really painful calculation to 2-loop. at the end of several weeks of calculations, everything goes away, and you do end up with these Gaussian numbers. So there's all kinds of magic cancellations happening. But actually, that was quite stupid, because if you really use this Kohl-Hopf transformation and work in that representation here of the KPZ equation, above 2 dimensions, you can sum this thing with no trouble whatsoever to all orders in perturbation theory. It takes, takes an afternoon, not weeks. And you end up with these answers. So that's believed to be the correct answers. All right, we are getting there. I was hoping to be only 1 minute over time today because I was going to go, but it's 2 minutes still. So let me stop here and say a few words tomorrow about conserved KPZ variance, and that's just going to be a few words, and then we're going into scale invariance and phase transitions into reaction diffusion systems, which I think I can happily cover tomorrow. Okay, do we have questions? All right, as I keep saying, catch me during lunch, breaks, dinners for questions if you have them. And I'll see you at those times and tomorrow. Thank you.